My name is Rute Bento, and I'm doing the presentation on the Portuguese work that we've developed for this project. This is a teamwork, of course, and these are the people involved in this work. And I'll talk about the numerical modeling of the wave energy potential for the Atlantic European coast. What we did was to use your earlier experience and data that we had from previous studies and develop upon that some work for this Marin project in order to determine the potential of the wave energy available in the areas that concern this project. I'll do my presentation divided in these points. I'll do a brief introduction on how we relate wave energy to waves, and a small introduction to the target areas. I'll then do a description of the wave hindcast system and the models that we used, talk about the validation that we did and the wave energy assessment, and how we relate the results that we get with wave energy converters, and then some concluding remarks. So wave power is proportional to the square of the amplitude and to the period of motion. Therefore, if we have periods of 7 to 10 seconds and amplitudes of around 2 meters, we can get energy fluxes averaging between 40 to 70 kilowatts per meter with an oncoming wave. Of course, nearer to the coastline, these energy values decrease due to dissipation, but this can be compensated with refraction or reflection, and it leads to what we call hotspots. Here we have a general image of the distribution of wave energy along the European coastline, and we can see that wave power increases from 33 kilowatts per meter of the southernmost part of Europe to up to 76 kilowatts per meter of Ireland. So the target areas were starting with Portugal. Portugal was chosen because it has a relatively high latitude and a long stretch of ocean, and it has a very narrow shelf. So it means that deep waters are relatively near to coast. And along its coast, it has several harbors and shipyards that could give support on devices maintenance and implementation and so on. We have also developed some technical scientific knowledge in this area, having implemented several pilot zones. For example, we have a Gossadora, which is composed of a set of 3 Pelamis wave energy devices with an installed capability of 2.25 megawatts, which means 750 kilowatts each. Unfortunately, this project has fallen mainly to the financial collapse of the majority owner. Although we have developed others, such as in São Pedro de Moel, which is an area between 30 meters and 90 meter water depth, with 320 square kilometers and an installed capability of 250 megawatts. And now we have also Peniche, which is composed of a set of 3 wave roller devices with a capacity of 100 kilowatts each. So Spain, moving to Spain, it has also a Western European coastline, and it's also preeminent in wave energy exploitation. We have Galicia here, with energy between 40 to 45 kilowatts per meter. We have the Cantabric Sea with 30 kilowatts per meter, diminishing from west to east. And thirdly, we have the north front of the Canary Islands with around 20 kilowatts per meter. Also, several prototypes have been developed here in Spain. We have the project in Cantabria involving a 40 kilowatt prototype buoy, the first phase of a larger project. We have the new seawall in Porto of Mitruki, which is based on the oscillating water column principle and involves 16 turbines with a total capacity of 300 kilowatts. BMAP is an infrastructure designed for researching and testing and also demonstrating wave energy converters. And the PLOCAN is a governmental consortium with the objective to build and operate an offshore infrastructure to facilitate research and speed up the technology associated. In France, in general, the wave energy resource is very interesting. In particular, the areas of the Pays de la Loire and of the Aquitaine present a wave energy flux of about 25 to 30 kilowatts per meter, far from shore. And they have now planned a test site of the Croisic as a part of the program CPER for the period of 2007 to 2013. For the United Kingdom, accessible resource in deep water was estimated between 600 to 700 terawatts hour per year, and the nearshore around 100 to 140, and several hotspots are identified along the coastline. They have already starting to implement 2 test sites, one of Cornwall, known as the Wave Hub test site, and the site of the Pembrokeshire coast. The Wave Hub project plans to develop a 20 megawatt grid connected infrastructure for the demonstration of small arrays of pre-commercial wave devices. And the Wave Dragon is for a 4 to 7 megawatt demonstrator, and a larger wave array is planned for deployment in several years' time. In Ireland, the mean theoretical wave power lies between 50 to 60 kilowatts per meter within 25 kilometers of Mayo and Kerry. And it falls rather sharply as one moves eastward along the south and north coast towards the Irish Sea, getting as low as 10 kilowatts per meter. Nevertheless, in winter months, we have regularly values that exceed 150 kilowatts per meter. They also have 2 test sites, Belmullet, which is a test site for wave energy converters at not at a scale level, and it's proposed to operate up to 20 years all throughout the year. And this is the layout of the test site. And in Galway Bay, we have a site for testing 1/3 to 1/5 scale devices because it has the ideal conditions when then compared to the offshore, to the open ocean site in a scale perspective, of course. So these were all the things that are already been done and already known from previous studies. We have developed this wave hindcast system. We use 2 models, WaveWatch 3 and the Swan model. They are both state-of-the-art, full spectral 3rd generation models, and they are based on the wave spectrum, of the evolution of wave spectrum in space and time and the conservation of action density. This is the equation that defines what I've said, and it also can be written in this form. And the first term will translate the action density evolution in time. The second and third, the energy propagation in 2D space. The fourth term will represent the angular frequency variation due to bottom effect and currents. The fifth term will translate the wave refraction due to bottom effect and currents. And the last term represents sources and sinks, such as bottom friction, white capping, wave-wave interaction, and so on. WaveWatch 3 tends to be more efficient at global scales, and Swan more efficient in shallow water processes, and that's why we couple them both. So for the hindcast system, the data that we used as input, we used for WaveWatch bathymetry from GEODAS, which is a NOAA database, and wind fields from the European Center for Medium Weather and Forecast, and we used the ERA Interim database. And for the SWAN model, we used bathymetry from JEPCO, and also a nautical chart for a Galway base case, and we used the same winds. So the WaveWatch was run for the North Atlantic, and the SWAN model was run for the nearshore areas. To validate our results, we used 17 wave buoys, all distributed along the coastlines. And the buoy data came from the Portuguese Hydrographic Institute, from the French network Candice operated by CETMEF, Spain's Puertos del Estado, UK Centre for Environment, Fisheries and Aquaculture Science, and also the Met Office, and Ireland's Marine Institute. The buoy depths range from 22 meters up to 780 meters in the Gran Canaria area. To validate our results, what we usually do is we do the time series and compare the simulated results with the real data, and we do scatter plots, and then we do a statistical evaluation computing the average values of measurements and the simulations, the bias, the root mean square error, scatter index, and Pearson's correlation coefficient, and these are the equations that express those quantities. In terms of energy, SWAN outputs the energy transport components, and afterwards we calculate the wave power by using those components. So these are the results that we got. We have results these are all for the coarse grids, and we have from 1-year simulation in Ireland to 10-year simulation in the Canary Islands. And the values that we look at it as more important are the bias, the root mean square error, and the correlation coefficient. And they have all very good results, but when we see bigger errors in UK and Ireland. And this might be, and we are doing the analysis at the time because of the input of the ice grid when we use the models. Nevertheless, if you see UK1, we have bias of 0.59 and UK3 0.76, and this can both be upgraded, if we can say that, when we do a zoom in on the coastal areas. So for the mean wave period, we realized that we had the same the rise in errors for UK and Ireland. But as I was saying, when we do the evaluation of the nested areas, the 0.59 goes to 0.44 in Pembrokeshire, and the 0.76 goes to 0.39 in the wave hub location. So we can improve these results with nested areas. Well, I'll go through some of the outputs that we get with that we can analyze when we talk about energy. For example, in the Canary Islands, we have done an average annual wave power with the SWAN simulations. You can see here the Canary Islands, and this is Gran Canaria. And comparing with previous studies, we have a good agreement with the wave values, with the wave energy values that we get. And we can see that different marine studies and ours conduct to the result that we have a power of about 10 kilowatts per meter at the east of the island of Gran Canaria. We also did theoretical maps for the average wave power for the Portuguese and the Spanish areas that I'm going to show afterwards. This goes from 2009 to 2011. These are monthly means. And we can see, having in mind that waves commonly come from northwest, and this reflects on the distribution of energy along the coast. And we can see also that the months most energetic months are February and November, with maximum values of about 70 kilowatts per meter and 90 kilowatts per meter, and less energetic is August with 10 kilowatts per meter. These are the nested areas chosen for Portugal, from 1 to 6, from north to south. These black dots are the points where we had maximum wave power, and we can have values up to 384 kilowatts per meter offshore Aguçadora, which is here. So we did the same to Spain, and we got more or less the same values that show that January and November have values reaching up to 70 kilowatts meter offshore and 40 kilowatts per meter near shore. And up 40 to 70 kilowatts per meter near shore, and the less energetic months are the summer months, with ranges between 10 to 20 kilowatts per meter. These are also the Spanish nested areas, from west to east. And we have, for example, this point here, with 545 kilowatts per meter, with a corresponding significant wave height of 7.46 meters. For France, we did the same thing, and we have also a good agreement with previous studies done. And we have January and December with mean values of around 40 kilowatts per meter. And here is the nested area. And they show that we have 20 to 25 kilowatts per meter throughout the year. For the for Ireland, I'm showing a different perspective of what we can take out of the results that we get. For example, for buoy 1 and buoy 2, we can see the directional distributions of significant wave height, and we can clearly see that Northern Ireland have incoming waves from north and southwest, while Southern Ireland are predominantly from west direction. And we can also see that bigger waves with bigger significant wave heights come from north in the first case and from west in the second case. We also did a study on Galloway Bay, and the wave energy potential of the results that we got range between 2 to 3 kilowatts per meter, which means that at a quarter scale, it's a good representation of what we can see at exposed ocean. So it is possible to gather information on useful performance data from the devices and ensure that the installation can be accessed and maintenance is easily done. Finally, this is all theoretical values. So when we look at these values, you have also to think about what it can be harnessed in reality. So when we talk about the wave energy converters, we have to study also other things. For example, we study the sea state occurrences according to the significant wave height and the energetic period. And we also study the annual wave energy corresponding to those sea states. And we can see that what occurs the most might not be the most energetic values that we get. So this has to be taken into consideration when we choose the wave energy converters and the place that we choose to put them on. So as concluding remarks, we implemented the wave prediction system using two wave models, WaveWatch 3 and SWAN, for the Western European coast. We took bathymetries from NOAA's and JEPCO's databases and wind fields from the European Centre databases. The results were validated with buoy data for 1 year or more. And we got outputs such as average annual wave power, monthly or seasonal wave power, maximum wave direction, maximum wave power locations, directional distributions of significant wave heights, wave activity and number of occurrences, and we compare it to the known power matrix of the wave energy converters. What we are doing at the moment is that after all this, the main objective is to get a 30-year hindcast for wave energy potential, as well as the wave energy atlases for the Western European coast. We are also doing some studies on coastal impact, although I haven't presented here. There's a poster outside, if you're more than welcome to go in and check that out. And that's my presentation. Thank you so much.